Hi everyone, welcome to the 38th video in the Weather Unlocked video series on hodographs. We're going to talk about what a hodograph is, how they are plotted, and what they can tell us about the environment. A hodograph is a plot of the wind speed and direction at multiple levels in the vertical profile of the atmosphere. Its name comes from the Greek hodos, which means way, so it is a graph of the way of the wind. We will discuss how it can be used to diagnose the potential for supercells, to determine the favored speed and direction of storms, and even provide insight about the potential for storms to form tornadoes. But first, let's talk about how the hodograph is made. First, we need to understand wind barbs, wind vectors, and the difference between the two. The most important difference is the direction the barbs and vectors point. Wind barbs lay in the direction the wind is blowing from. So, if the wind is blowing from the west, the wind barb will be laying to the west of the point where the wind was measured. Wind vectors lay in the direction the wind is blowing to. So, for a westerly wind, the wind vector would point to the east. Wind barbs and vectors also depict the wind speed in different ways. Wind barbs will have more barbs or flags with faster wind speeds, and wind vectors will be longer. The direction of the wind is named for the direction the wind is blowing from, so the direction the wind barb points, at its clockwise angle from 0 degrees or north. That means a westerly wind is blowing from 270 degrees. On the left is an example of both wind barbs and wind vectors illustrating the wind speed and direction at various levels in the atmosphere. Each barb on the wind barb corresponds to 10 knots, and each flag corresponds to 50 knots. So, the wind barb at the surface is showing a 10-knot wind speed, and the wind barb at 6 kilometers above the surface is showing a 60-knot wind speed. Notice that the corresponding wind vectors get longer the faster the wind speed. Also notice that the vectors point exactly opposite of the wind barb at the same level. To create the hodograph, all of the wind vectors for the column are plotted onto the same 2D plane on a polar coordinate system. In a polar coordinate system, instead of having x and y axes, coordinates are given in degrees and distance from the origin. This system conveniently resembles a compass, and we can more easily plot wind speed and direction this way compared to a square plane. Directional convention on a hodograph is the opposite of how we usually describe wind direction, to account for how wind barbs and wind vectors mirror each other. Wind is named for the direction of the wind barb, but hodographs are made up of wind vectors. A wind out of the south would be coming from 180 degrees on our typical compass, but plotting it on the hodograph would result in a vector pointing north. But we need both the barb and the vector to be defined as a 180-degree wind. Therefore, 180 degrees is north on a hodograph rather than south as it normally is on the compass. This way, a 180-degree or southerly wind has a vector with the same angle from 0. Each wind vector from our vertical profile has a length and an angle from 0 or south. If a point is plotted at the tip of that vector, its coordinates, which are the angle in degrees and the distance from the origin, correspond to the properties of that vector, and the characteristics of the wind at that level are plotted. A hodograph is created when a point is plotted at the end of every wind vector from each level and then connected with a line. Each point is typically labeled with the height above the surface it corresponds to in kilometers, so that when any point on the hodograph is being evaluated, it is known how far off the ground that wind was measured. The farther you get from the start of the line, the higher you're getting in the atmosphere. Hodographs provide a quick way to determine at a glance how winds are changing speed and/or direction with height. This is the definition of the wind shear, and certain measures of wind shear can help us determine the types of storms that may form, which direction they'll move, and what kind of hazardous weather threats they may be capable of. This is an atmospheric profile measured from a weather balloon released in Norman, Oklahoma on May 6, 2024 at 6 p.m. local time. These balloons are released from 92 different National Weather Service offices twice a day, and the data from each flight generates a skew-T diagram and a hodograph. For more on skew-T diagrams, see Weather Unlocked video number 3. We won't talk about the data generated from the skew-T since that is covered in the skew-T video. These are known as the thermodynamic variables. We will discuss the variables on the right, which are calculated using the hodograph, also known as the kinematic variables, or variables that pertain to the way things are moving, rather than temperature and moisture in the case of thermodynamic variables. The vertical profile of wind barbs that we talked about previously is displayed on the side of the skew-T, showing the wind speed and direction at various heights as the balloon rose through the atmosphere. As illustrated in earlier slides, these wind barbs were turned into vectors, plotted on a polar coordinate plane, and their tips connected using a continuous line to create the hodograph in the upper right corner. You can visualize that the vectors that created the hodograph would lay in the opposite direction of the corresponding wind barb at the same level. These vectors are also longer the faster the wind is, or the more barbs and flags there are on the wind barb. Longer vectors result in the endpoint being plotted farther from the origin, depicting a faster speed. For example, the wind vector at 2 kilometers resulted in an endpoint landing at around 40 knots, while the vector at 6 kilometers had an endpoint landing around 60 knots. We mentioned that wind shear is the change in the wind speed and/or direction with height, but now we will demonstrate how wind shear over more specific layers can be calculated using the hodograph. Wind shear can be calculated between any 2 levels. This particular software used to generate this graph has calculated shear at a few crucial levels automatically. To calculate shear between the surface and 1 kilometer above ground level, draw a vector from the surface point on the hodograph to the 1 kilometer point. Shear has both a speed and direction depicted by this vector. As listed below, there are 34 knots of shear between the surface and 1 kilometer. The amount or magnitude of shear corresponds to the length of this vector. It can be calculated by subtracting the wind speed at the top of the layer from the wind speed at the bottom of the layer. We can estimate based on the labeled circles of the coordinate plane that the wind speed at the surface is about 10 knots and the wind speed at 1 kilometer is about 44 knots, giving us the 34 knots listed at the bottom for the surface to 1 kilometer shear. You can also visualize laying the shear vector along one of the axes to estimate the magnitude of the shear. The direction is not listed, but if you imagine moving the vector to the origin, it would point at about 210 degrees due to the typical compass conventions being flipped on the hodograph. So, since the shear vector is from the southwest to the northeast, this means winds are turning clockwise as you go up from the surface. This shear calculation can be done for any layer. One particularly useful measure of shear in forecasting is the 0 to 6 kilometer shear or deep layer shear. The magnitude and direction of this shear vector is helpful for determining the most likely type of storm when used alongside other measures of the atmosphere. Another use for the hodograph is determining how quickly and in what direction storms might be moving once they form. First, we determine the mean wind using a number of methods defined in the research. This is the average direction of the flow and the direction that developing storms will initially move. Next, we can calculate the speed and directions of storms that move to the left and to the right of the mean wind vector. This is best visualized by imagining that you're standing at the beginning of the mean wind vector and looking in the direction of the mean wind. Right-moving storms would be moving away to the right of you, and left-moving storms would be moving away to the left. Calculating these motions is a bit involved, but most of the time they would be plotted on the hodograph for you. One of the most useful applications of estimated storm motion is using it to determine storm relative helicity, or SRH. SRH is a measure of the potential for supercell updrafts to rotate. Similar to shear, it is calculated over a layer. To calculate 0 to 1 kilometer SRH for a theoretical right-moving supercell, the storm motion vector and a vector from the storm motion point to the top of the layer of interest are used. The value of SRH is calculated using the area traced out between these two vectors and the hodograph. Here, 0 to 1 kilometer SRH has been calculated and printed at the bottom. SRH can be calculated for any layer and for either the left-moving or right-moving supercell. Negative values of SRH indicate that left-moving supercells are favored to develop, and positive values indicate that right-moving supercells are favored. In this case, nearly all of the shaded area lies on the right side of the hodograph, and the SRH value is positive. This means right-moving supercells are more likely than left-moving supercells, assuming that the rest of the environmental characteristics support the development of supercell storms in the first place. For more information on what makes a storm a supercell and on other types of storms, please see Weather Unlocked video number 20. The amount of SRH tells us how much potential for rotation there is in a layer, and high values of SRH in near-surface layers may correspond to a higher potential for storms to produce tornadic circulations. Thanks for tuning in to the 38th Weather Unlocked video all about hodographs. Be sure to keep up with us on our website and social media pages, and stay tuned as we continue the Weather Unlocked series of videos.